The views survive themselves and not of interest usually. What's of interest are the contrast, right? Although we could state that this is our null hypothesis. Levels don't matter. It's usually the contrast of interest. Okay. And we did talk about the Kruskal-Wallis test. Are there any questions on that? That's a test. Maybe we should look at that.
Not yet.
Here's a huge data set, okay? That's included the Kruskal-Wallis test where usually. Remember, we just combine the data and rank it. Okay? So you could just rank it as it is. It really helps. If you want to do it by hand, it helps you resort the data. Let's just do that. Do you have any questions on this? And you can just go through the numbers. There's 2 8s, right? Ranks 3 and 4 are gone. 1 and 5. Six and 7. 12. So you just combine the data and rank it for the Kruskal-Wallis test, and then you just add up the marks. Do the average. So this would be what? 3, 6, 12, 20 and a half. So the average rank was what? And then here is B15, what, 27, 40, 54. And then the next would be 16, 27, 30. So now I have my average ranks, and this could be done with a hand calculator. Now we're on the way. The average rank, there are 10, 14 observations. So the average rank is 14. The average rank would be 10 plus 1 over 2. Well, it's not that. It's 8 is just 12 over n times n plus 1, right? And then we get the sum of 10 times the average minus Any questions on the Kruskel-Wallis test? It's really straightforward, and that's doable on an exam part of it anyways, if you have very small data. Any questions on that? And then it's one of the chi-squared critical values, right? And then it's k minus 1 degrees. So in this case, for a 5% test, we might look at chi-squared critical value of 2. It is distribution free. There are some tables for very small samples for distribution to get the critical values. Almost everyone uses those. Yes, I'm sorry.
Can you, if we can focus on, what is it, X2 with a monitor?
Chi-squared.
Oh, it's chi-squared.
I don't know, chi-squared. Okay, chi-squared. Now, of course, the big trouble with Kruskel-Wallis tests is you don't have the effects. You can do there are multiple comparison procedures based on ranks. I always thought they were. I don't think people really want to do that. I mean, we designed this experiment. We're after the effects. It's nice you have a distribution pretest for the hypotheses, but I don't think you want to do the comparisons. I think we want to go back to the effects, estimate the effects, and estimate the size of the effects, like a standard error. Actually, in social sciences, that's pushed a lot. They want an effect size. Okay, I'm not sure why. They made it very complicated. For a while, I thought it was a standard error. I got arguments, not arguments, but discussions with Brad. How long is this? The standard error? That's the way scientists, right? That's a 68% confidence.
Isn't something designed for meta-analysis?
We do the same thing for meta-analysis, and we get it into a standardized form and then put it together. Actually, that would be a good topic for this. So I think this is really what you're after, and then you just get there's a multiple comparison problem. You can't get away from it. If you want to do all comparisons, it's k choose 2. Almost like k squared, right? It's 2, right? 2. So it gets large very, very quickly. Again, you might have a placebo, so in that case, there's k minus 1 comparisons. And then you're going to have overall, you're going to have a slippage of confidence, right? I don't know if we talked about this or not. Well, we could look at the Bonferroni fix. We're just looking at the slippage of confidence for 2 confidence intervals. You can tell me what the Bonferroni fix is. First, I guess this is Bonferroni. And again, you can see with 2, so you have 2 CIs, right? So you have theta 1 and I1, and theta 2. Okay? It doesn't matter what the parameters are or what the intervals are. I just know that the probability of this to the probability of this is 1 minus. Okay? So if alpha is 5%, then I have two 95% confidence intervals. The problem is that's not the confidence statement I want. I want the statement that theta 1 is an I1 and theta 2 is an I2. This is the statement I want. Okay. Simultaneous. And is intersection. How do you get a handle on that? You don't, but then you think, I'm in probability, and probability always has an edge over mathematics, because you can always just look at the complement. Okay? If it doesn't work, I just look at the complement. Usually you can't do that in mathematics. But it works like a charm in probability. Okay? So now I'm looking at the complement. That's the complement, okay? And I like to say that comes out to null now. With the complement, I've changed an intersection into a union or a NOR. Okay, and then we stick to an inequality. It's like I want the probability of A or B, right? But I don't want to go back to the intersection. That's where I was. I couldn't solve it. So I just add the football twice. In other words, the probability of A or B is always less than the probability of A. And I got a negative sign up here, so the inequality goes the other way. And I know what those are. So my overall confidence, I did the confidence. My overall confidence can slip to 1 minus TL. So it didn't come out to 1 minus. So what's the von Neumann fix? How can I make that 1 minus alpha? It's easy. Don't think too hard. I want to come out to 1 minus alpha. And that would say my overall confidence is greater than or equal to 1 minus alpha. So if alpha is 0.05, then I have 95% confidence. There it is. I might even have more. So how can I do that? It's easy.
You add alpha?
Pardon?
Add alpha back?
No. How can I change it so that it comes out to 1 minus alpha?
Subtract.
I want 1 minus alpha.
Guess you could put in half the alpha to begin with.
Exactly. You just cut alpha by 2 and it works. All right? The one for honey fix is that simple. Oh, no. That confidence interval 97.5% ones. It works. That's the Bonferroni fix. And if you had K confidence intervals, you just cut alpha by K. This inequality will work. So if we have, I should use K because we have K treatment. I guess, how about M? Let M be the number. C values 1. M. Now you're going to cut alpha by 2. So that's the critical value. Use this. We can do on teams. But you could use doing Z's too, so well, you can see what's going to happen. These are going to get huge. It's just we could do it. So let's just have M go from 1 to 20, 2 to 20. Let's use a Z critical value. No, let's use a Z critical value, okay? We'll use a Z critical value, so that's Q. Do that 95% confidence, okay, so I want the upper, make it large. There we go. So if I only have one confidence interval, it's 1.96, right? And then if I have 2, it's up to 2.24 already. And then here I'm doubling it, right? So here's my confidence interval, which was double the size. And here it's getting close to what? 150%, right? It's getting bigger and bigger. So Bonferroni's, who loves Bonferroni confidence? Administrators, right? We're not going to see anything because we have to do 95% confident. So we're doing 60 comparisons. Our confidence intervals are real wide. See, they swallowed up to 0. You start with one confidence interval, and 0 is not in it. You say, it's significant. And then you say, well, I have to do a Bonferroni to be absolutely sure. So then it gets bigger and bigger, and it's swallowing up the zeros. So then we come in significant. That's the bad news. But if you want overall confidence greater than or equal to 95%, the Bonferroni will work. Okay, it's a very simple procedure. It's used quite a bit. A lot of researchers know that's what's happening, I mean, they don't want to use it. Okay, any questions on the von Ferroni? So it's an easy one to use. You don't really need new critical values at all. Okay, so now we have the von Ferroni. So this is one. This is one. Maybe after the Italian, right? That's actually that inequality that's sometimes called the von Ferroni inequality. Although I've learned it as Boole inequalities. Von Ferroni means in Stuckman's. Okay? What's the second one? The second one is actually due to Tukey. John Tukey came up with a really neat way of doing it. There's a portable procedure, it's called the Chauvet procedure, which hopefully no one ever uses because that's even wider than von Ferroni's. So Tukey came up with one that'll work. In this case, is exact if it's balanced, but if it's unbalanced, the fix isn't that bad. It's due to a guy named Kramer. Whoever it is, that led to Kramer. Now I'll go back to the comparison, right? So for the von Ferroni, maybe I'll be using T or Z. And then I'll have some degrees of freedom, because the problem I'm talking about is the n minus k. And then I'll have to have an estimate of scale. It's either sigma hat or tau hat. And then we talked about this last time. This would be for I and I prime. But that would be like the von Ferroni error term, right? And then Tukey Kramer, it just changes this, and for some reason Tukey these are the studentized range. Tables mess. Here's Kramer K and N minus K. This is for all K choose 2. It does not differentiate, but then the rest of it is the same. And these are studentized ranges. You can get an R. You are something. So you don't have to go to tables. Okay, for class, it's in the package, okay. Our fit uses 2 Kramer. We'll never be have to use the table in this class. A third way is in many ways, but this will be exact, okay. So the confidence here will be, actually if you had normality and balance, it will be exactly 1 minus alpha. Here the confidence is greater than or equal to 1 minus alpha. And then the third way is actually the way I like Fisher's protected L, least significant difference. consists of two pieces, test H two, reject H naught, this is the overall test. If we reject H naught, just do the usual constants. Filter spot. Now, the trouble with this one is it doesn't have an overall confidence rate. The test does give you some confidence in proceeding. See, when you reject that hypothesis, then you're saying there's a difference. There's at least a difference. So I need to find it. And then these are going to be much more powerful than either Tukey or Bonferroni. Usually in most problems, as you will see, Bonferroni and Tukey are about the same. These will be, of course, much shorter confidence intervals. There's no overall confidence. Okay, so then how are we going to compute them? Let's go back to our part problem, right? In this class, I guess there's two ways of doing it. I don't think Minitab can do it. You can use the web page, okay? RGLM actually will do this. Or you could use R, okay? So let's just go over R. R fit needs, I think it's part of R fit. Special function. It's just one way. And then you have to put the response in. Let's go back to the problem. That's all you need, and then the method equals. And then it could be, I think the only ones we have are 1, 2, 3, 1. Or it could be nothing. Nothing is Fishers. It's like Fishers is default. Okay? I've got 3 of them, of course. Okay, so here we go. Now we can decide which car we're going to buy. Finally, Okay, so just so in our fifth, right, and then, get the data in. So there's my speeds, right, and here's my cars. And it's Acura, Ferrari. Lotus, Porsche, and bike. So this is our last chance. Oh, and also, the command will do an F test based on the linear model. Whereas the only one we talked about is, well, it depends. I don't want to switch it. There's an F test. Let's call that W. I think maybe we talked about this. It's just a drop in this word. So the command will also do that F test. Okay, so let's do. Okay, so it's just already. Oh wait, I got that. No, that's a summary. Stop sequence. Okay, this is summary. It's two commands. Okay, you have to do the fifth and then the summary. That's what you do. So going back to the yard, it's just one way of going. And then response and then loop. There's a schematic on there, just but there's the F statistics, it's 14. All right, and the p-value is 0 to many places. So it's highly significant, just like the Kruskal-Wallis test, okay? So we're convinced there's a difference, that's for sure. Now this running like the 2p, so I just need to do some. And then I have to put that fit, wherever I call it. Let's just do the 2p. This is the last chance. It's 2 and 4, right? Oh, you can't decide. It's not. difference between the Ferrari and the Porsche. Ferrari is ahead by 3 miles an hour, but it's not significant, okay, it's negative. Minus 4.8. So in this negative range, the Porsche could be winning, right? In the positive range, the Ferrari is winning. So it's inconclusive. I know you feel bad. That's why I couldn't buy the car and stuck with it. Look at something.
I know that choice between the Porsche and the Ferrari was a hard one.
Yeah, it's too hard for me, I can't. So I'll set the conquer Western final. But notice it beats the other three. So let's look at the Ferrari, it's 2, right? So it certainly beats the Acura, right? And then it beats the Lotus. And, it beats the last one. And the Porsche is 4, so what does it do? Yeah, the Porsche wins on the Lotus, but the Porsche doesn't win. And the mag, it's often done, is to just draw a real number line and lay off those means. That's the one thing. Is it in the other thing? Oh, we should talk about how to do that. We don't have it. But anyways, you lay off the means and then, well, you know that the Porsche, Ferrari, here was the Porsche, and then there was the other 3. Then you underline them if they're not significant. So that tells a story of this schematic. And actually, I guess the Viper is next. Those are not significant. Okay. Now you could do a summary of not all is lost, right? Because that would be fiction. So in Fisher, it was about 2 and 4. Fisher is still it's minus 2.4 to 8.5. The other one is minus 4.7. See, it's a much bigger confidence interval. It's much smaller at these Fishers. I think the Bonferroni will be about the same trial. So we're looking at minus 4.8 to 10.8. Yeah, it's a little bit bigger. Often they're about this. Now, if you just had a placebo, you don't in this case, but if you did, then you'd only do K-1 comparisons, and the Bonferroni would get shorter. So you'd probably use the Bonferroni. Okay, any questions on that? Now, the other way to do it, I have the data stack once. So the other way is to use RGOM as well. See, it does stuff. I can draw. So this would be your alternative, right? If you don't want to use R, you're not using R, right? It's all kind of cross. We'll just do it too. Yes. It should have done it, I'm not sure. Maybe I have to click something. It's hard to see for some reason. It should have done it. I'll try one for me. See? Looks like it's dead, so I'm not sure. It does the up test, but it doesn't. I'll have to check that.
It might be low down.
Pardon me?
It might be low down in the frame.
Yes. I don't see it. It was working, I'll have to. Okay, I'm not sure what else. Okay? So it's a little bit hard to test on it, right? I mean, I could ask you for like critical values and things like that, if you'd like a one. This is not really being supported this one way. I get all these nudges. Actually, it seems like a lot of people in Australia use this. So they don't know that when you go to the page no longer works, it's in trouble. Research for this. I've gone to R, okay, it's hard to keep a web page alive. You need good professional knowledge. I lost. Yeah. Then Kim decided she wanted to work in the pharmaceutical industry. So she made a couple $100,000. So, $100,000. Kim was working in the pharmaceutical industry for years, and then she decided she would try academia. So she took a position in the biostat department. I told her she's going to get some sticker shock. And she did. And her husband lost his trial, and that was the end of it. Back to pharmaceutical. She said, "Oh yeah, you told me about sticker shock. I didn't know something." Okay. Any questions on that? So I'll look at that and I'll see if I can figure out what happened here. I'm not going to really worry about it. Since it's like we've come to the end, right? I mean, not in this hard. So, any questions on the idea? So that's the basic for the one way. We talked about an overall test for Cruscowalis. We also have an F test we can use. Okay, we can get it with RGLM, or we can get it with FIT. We can compute. We have a multiple comparison procedure, and it's estimating the effects, and we'll talk a little bit about how to run that, especially in our FIT. Okay. So the next thing I'd like to do is in fact, while we were at it, we could let's look a little bit. There's a couple things we can do with this model, and one thing we could do is analysis covariance. It's a simple case because it's still just a one-way layout, and you have a covariate. We can talk a little bit about the adjusted analysis. It's used quite a bit. And this often comes up in practice because you do the design, but there are some covariates of interest which you know affect the response. So you'd like to try to incorporate those into the model, okay? And we could just look at one covariate. So the basic setup is still a one-way ANOVA. We can do it for other designs too, but this is all in this class. So we have a one-way ANOVA, we have K levels, right? That stays the same. And the size of the response. Covariate. name is, this actually varies with the response. So you think the reason we're even looking at it is there's some relationship, it might be a very strong relationship. Let's say that the response is Y, okay, and covariate is X. You know, you might be looking at a treatment for, a good example would be a treatment for blood pressure. The treatments for blood pressure. So I don't know, maybe you have 4 treatments. And then weight is a factor, right? Often an important factor in blood pressure. So in this case, Y would be the blood pressure. Another one that's often used is you do have a response which is taken at baseline before the experiment begins, right? Then you have like the treatment phase, and then you take the response after. Well, the response at baseline is often used as a covariate. Response is that. You can certainly have more than one covariate, you can have many covariates. Okay? We could just focus on one covariate. Then when you do the F test, you adjust it. You adjust it for the covariate. That's called an adjustive analysis. And often the covariate is going to explain noise, so it's going to reduce variation. And that means what? That means smaller confidence intervals and larger test statistics. So usually the adjustment works. Okay. Now, there's one thing we have to worry about, and that is that the treatment and the covariate interact. Many experiments you say, well, that they should never interact. But it doesn't hurt to look at it. So what would that mean? Well, in the simple case where you just have one covariate, it's straightforward. So you have usually response, right? So this would be like treatment 1. You just plot the response in the covariates. First order effect would be linear, so you can create a model. So maybe you have the scatter plot, and as the covariate goes up, the response goes up. So this would be the treatment 1. Well, then you can do the same thing for treatment 2. Well, there's 2 things that can happen. For treatment 2, it could be sort of parallel. Well, this is great because no matter where you are in covariate space, you have the same difference. If you're here or here, it's just like you have one difference. Okay? This is the best. This is the ideal model. There's no interaction between the covariate and the treatment. Now, of course, it's not going to be perfect. But then you can have a situation where they do cross. So this is treatment one, and then this is treatment two. Say bigger is better than, in this side of covariate space, one is ahead, right? And on this side, two. So then, you know there's a gray area, you can't decide anything. Now you have problems, now there's not one number. So I'm gonna have one estimate in this case. To treatment one and treatment two. Here I don't have that. Now, there's ways of going around it. You can do, there's a method called pick-up point. Yeah. It's pick-up point. Where you select points and then see if there's a difference. And then your inference is just on that point. Okay. So you select these pickup points. Inference goes, let's just do this, treatment two. X naught's the select point, and then treatment one, and X naught's the select. So you can certainly estimate this parameter from the fit, and then you can get a confidence interval for it too. Okay. Like we talked about, right? We talked about getting confidence interval with respect to value line at a specific X. So you can do that. Okay. I don't think we'll get into that in this class. But this we have to be aware of. So what's the strategy for testing here? You want to test for interaction first. And then, if you fail to reject, then you probably want to go on and test for the treatment. If you reject them, then it's not clear what you want to do. You could do these pickup points. Some people are really uncomfortable with pre-testing, but I don't understand them. You have to do this. Right? You can't be blind. And if they're sort of parallel, you convince yourself that it's not true. You definitely want to test for effect. You want to do the adjusted analysis. This is what's done in practice. Okay. This is going to be. Careful, it's not the same analysis we did. This would be the adjusted analysis. Okay. So that's where we are. Famous snake data. It's out of a book. I don't know if it's. I think it's. I talk about it as a little bit. Anyways, they had an experiment on treatments for getting rid of snake phobia. And it's 4 treatments. The first one would not be anything. And so the response is how close you can get to the snake without feeling uncomfortable. And then covariate is baseline measure. Lots of stuff. This would be the first treatment, okay? And, it's a placebo. And, so this guy got within 25 feet initially, and within 25 feet the second time around. And this guy, he got within 10 feet first time, but then the treatment, he got hit within 30 feet the second time, whatever this number is. I can't see it. So there's no trend in the data for placebo. And the other ones, here's 2, 3, and 4, there is trend, okay? There's a lot of outliers, but there is trend. So what can you say? If you didn't have placebo in, they might be parallel, although you want to put them on the same plot. But then you could test that. With placebo in, though, there's no way that these are parallel. It's an interesting data set because the least squares procedure fails on a test of interaction. So the analyses would be different. Okay, for least squares, you would say, oh, there's no interaction. I'll just look at an overall treatment effect. And, for the robust way, you wouldn't do that. Okay? As you'll see, we really reject the charm. There's also some heteroscedasticity in the data too. It's not definitely an example. This is a cute problem. You can see the outliers. There's outliers. There's some really bad. It's like this guy. Too. Well, actually, he did much better. He really got over his fear. Yeah, this goes. No, that's how close you can get. It's worse. Actually, the first time was good. Probably touched it. Okay, so 2 words on it. Yeah, we have a short quiz. So we'll be up definitely through the crustal walls. So there's true regression. I'll look at my notes. Okay, so we'll finish analysis covariance, and then I think we should look at the two-way a little bit. Okay, and then I think I'll come back to the one-way model to look at ordered alternatives. Oh, and I want to look at the randomized block. So we have what? We have Tuesday, we have next week, and the week after, right? So we have like 3 lectures left. Can't do too much on the last lecture. So 3 lectures, we'll probably get through those topics.